Imagine climbing a staircase. You start at the ground floor, you keep climbing as long as you have not reached the top, and after each step, you move one level higher. Java has a built-in structure that works exactly like this staircase. We call it the for loop, and it lets us repeat code a specific number of times. Every for loop is built from three simple pieces. First, we set a starting value. Second, we write a stopping condition. Third, we add an update step. Let us write our first for loop in Java. We create a public class named main, and inside it we add the main method signature. Next comes the for keyword, followed by parentheses holding our three paths separated by semicolons. We initialize an integer I to 1, set the condition that I must be less than or equal to 5, and increment I each time. Inside the curly braces, we print the value of I. When the program runs, Java checks the condition before every cycle. It starts at 1, then steps to 2 and checks again. The execution continues through 3, moves to 4, hits 5, and finally stops when I become 6. You have seen how the for loop controls repetition with a clear start, condition, and update. Next, let us look at the while loop. Now that our for loop is printing numbers upward, let us try something different. Imagine you are walking toward a door and you keep taking steps until you actually reach it. You do not count the steps ahead of time. You just move forward while the destination is still ahead. This exact behavior has a name in programming. We call it the while loop, which repeats a block of code as long as a condition is true. You might wonder when to pick this over the for loop we just built. Use the for loop when you already know exactly how many times something should repeat. Use the while loop when the number of repetitions depends on a changing state or a dynamic check. Let us watch how our countdown actually moves through the steps. We begin at count equal to 5, then slide down to count equal to 4. Next we step to count equal to 3, followed by a move to count equal to 2. After that we reach count equal to 1, and finally the check fails, so we exit the loop. Now let us add this logic to our program right after the for loop finishes. We insert a comment to mark the new section, then print a header line to separate the outputs. Next we declare an integer variable called count and set it to 5. We start the while loop checking if count is greater than or equal to 1. Inside the block, we print the current value of count, then decrement count by 1 so the condition eventually becomes false. Finally, we close the loop block with a brace. You have now seen how the while loop handles repeating tasks with a pre-check. It keeps running until a condition turns false. Next, let us look at the do while loop. Now that we have seen how the while loop checks first, let us look at a different approach. Imagine you are testing a new mobile app. You always open it at least once before deciding to keep it. That is exactly how our next loop works. We call this the do while loop. It guarantees the code inside runs one full time before the condition is even checked. Let us watch how it steps through three numbers. First, I starts at 1 and prints immediately. Then we check the condition and step to the next number. Next, I becomes 2 and runs again. We check once more and proceed to the second step. Finally, I turns into 3 for the last run. After that final check fails, we exit the loop completely. Let us append the do while block to our main method. We declare and initialize I to 1. Then we add the do keyword and brace. Inside we print the current value of I. Next we increment I by 1 after printing. The closing brace ends the loop body. Finally, we close with while and a semicolon. Because it always runs at least once, this loop is perfect for two common tasks. First, validating user input until a correct value arrives. Second, displaying a menu that must show up before asking what to do next. You now know how the do while loop guarantees execution. Next, let us look at break statements. We will see how to stop early when needed. Now that our loop is printing numbers, let us add a way to skip steps. Think of a factory conveyor belt moving packages along an assembly line. We have the belt itself carrying items forward and one package that needs attention. The worker then pushes it off the side, diverting it away so production continues without pausing. In Java, that push-off action is called continue. The continue keyword tells the loop to skip the rest of the current iteration and jump straight to the next one. Sometimes we do not want to skip just one step but stop the whole process early. Imagine a teacher standing before her class of students. If she finds the exact student she needs, she stops counting completely. She then shifts focus to the daily activity board. In Java, that hard stop is called break. The break keyword immediately terminates the nearest enclosing loop, so no more iterations run after that point. Let us watch how these two keywords shape the path of a simple counting loop. Restart at I equals 1, moving to I equals 2, then reaching I equals 3. At 3, continue kicks in and skips sprinting, jumping straight forward to I equals 4. Next comes I equals 5, but break triggers here and cuts the flow completely, ending the loop right there. Let us add this to our program under the comment control flow example. We write a simple loop from 1 to 5, which will test our new control keywords. Inside, if I equals 3, we skip the rest of that cycle, so the print statement never runs for that number. Right after, if I reaches 5, we stop completely and exit the loop early to avoid unnecessary iterations. Otherwise, we print the number to the console as usual, and finally closing the loop body finishes the block cleanly. You have now seen how break and continue give you precise control over loop execution. This concept of loop control lets you direct program flow exactly where you need it. Next, let us look at nested loops and how they interact. Now that our loop is printing numbers and skipping steps, let us put one loop inside another. Think of a simple schedule. We have weeks on the outside and we have daily tasks on the inside. The wiki folder holds the daily task lists, so every single day finishes before the next week begins. This structure has a specific name in programming. We call it nested loops, which means one loop sits completely inside the body of another loop. Here is how the computer actually runs them. The execution pointer moves to the first outer step and then it drops into the inner loop to run all its iterations. Once that finishes, the pointer climbs back up to the second outer step and repeats the whole cycle. Let us add this to our program right now. We write a comment to mark the section so we can easily find it later. Then we open the outer loop that counts rows, which will control how many lines we print. Inside that block, we place the inner loop that counts columns, and it handles each number across the line. We print the product of row and column followed by a space, keeping the numbers aligned side by side. We close the inner loop block here to finish that row. Next, we call println to jump down to the next line, which pushes the cursor forward. We close the outer loop next, and finally we close main and the class itself to finish the file. When you run this code, you will see a neat grid of numbers appear on your screen. The first row prints 1, 2, and 3. The second row prints 2, 4, and 6. The third row prints 3, 6, and 9. This is exactly how nested loops build patterns or tables step by step. You have just seen how nested loops stack inside each other to create structured output. Try changing the limits to build a 5 by 5 table on your own machine. Keep coding, and I will see you in the next one.